Alright, now we'll start with the next chapter, that is mechanical properties of fluids. Fine. Now, any substance that can flow is called as fluid. So both liquids and gases collectively are fluids. Fine. Okay. Now, what is the basic difference between a solid and a fluid? Or why a solid does not flow and a fluid flows? Okay. Now, let us see this example. Now, suppose I have a solid cube. I have a solid cube over here. I am taking this part of the cube. Okay? This is a solid cube, and I am taking this part of the cube. I am considering only this part. Fine. So this part of the solid is in equilibrium. That means the forces acting on it should cancel each other. Now, let us say that its weight is W. It will be acting in the downward direction. I will resolve its weight into two components. One is perpendicular to the section that we have taken. Let us say Wn, N for normal, and the other is along it. Let us say Wt, T for tangential. Okay? Okay. Now the normal component will be balanced by the reaction by rest of the solid on it in this direction. What about the tangential component of the force? Who is balancing it? Now look here, the tangential component of the force or the tangential component of the weight will try to pull this part in the downward direction. It will try to rub the surfaces against each other. Rub this surface against each other. So there is a shear stress acting on this part. Okay? So this is nothing but the shear force, we can say, acting in this part. So who is resisting this motion? There must be some counter force in the opposite direction that is resisting this rubbing of the surfaces. Who is resisting it? The shear stress developed between the surfaces will resist this tangential component of the weight. Getting this? So the solid will not flow because it can resist the shear stress, or we can say that shear stresses can get developed in a solid. Fine. But can we have a cube of a liquid? We can never have a cube of liquid. Obviously not. But why not? Because like solid, if I consider this part of liquid, its weight is in this downward direction. It has two components, suppose normal and tangential component of the weight. Fine. Now over here there is no one to balance this tangential component of the weight, because shear stresses cannot get developed in a bulk of liquid. So if any surface tends to rub against another surface in a liquid, there won't be anyone resisting that motion. It will simply flow in that direction. Fine? Getting this? So we can say that tangential forces will never act on a liquid that is at rest. Because if tangential forces are acting on the liquid, on any part of the liquid, that part of the liquid will start flowing in that direction. because there won't be anyone who is opposing that force. Getting this? So shear stress cannot be developed in a liquid, or we can say in an ideal liquid. In viscous liquid, there are some amount of shear stresses, but again that amount is very small. Okay? And this is why liquid flows. Getting this? Because shear stresses cannot be developed in the liquid. Fine? Okay. So, or we can also say that tangential forces will not exist in the liquid. Okay? Okay. Now, take this example. Now, suppose I have this container over here and I have some liquid in this container. Fine? Okay. Now, let us see this part. Now the liquid will apply certain force on this wall of the container. Now that force may be in any direction. Suppose at this point there is some force acting due to the liquid on the wall of the container. Fine. Now I am magnifying this figure. Now suppose that force is in this direction by the liquid on the wall. So by Newton's third law, the wall will also provide equal amount of force to the liquid in opposite direction. Right? Because if I push this board, I am applying some force. The same force is being applied on me in the opposite direction by the wall. In the same way, suppose this is the force applied at this point by the liquid on the wall. The wall will apply a force on the liquid in this direction. Right? So I can have two components of this force, horizontal component and vertical component. But as we have said that tangential forces cannot exist on any part of the liquid, because if there are tangential forces, the liquid must be flowing in that direction of the force. Over here the liquid is stationary, it is stagnant. So there should not be any tangential force acting at any part of the liquid, and hence this force will not exist. For that to happen, the liquid will apply force on the wall of the container in perpendicular direction only, because then only the wall will apply force back on the liquid in perpendicular direction, and hence it won't have any tangential component. Getting this? And hence the liquid will always apply force to any container of any shape such that the force acting on that container is always perpendicular to the surface of the container. Getting this? Or if I consider any part of the liquid itself, this is the part of the liquid. Now forces acting on this part due to the surrounding fluid will always be again perpendicular to the surface of that part. Or if I put any object in the liquid, if there is some object in the liquid, even on that object the forces applied by the surrounding liquid will be such that these forces are always perpendicular to the surface at that point. Getting this? Okay. Fine. So please note down some important points. A fluid means a substance that can flow. liquids and gases collectively are called fluids. A fluid either has no rigidity or its rigidity is very low. The shear modulus of fluid is 0. In simpler words, fluids are substances which cannot resist any shear force applied on them. In any fluid, the only stress that can exist in the bulk is normal compressive stress. In bracket write down, called as pressure. Fine. So if I take any part of the liquid or any point inside the liquid, the forces acting on that point will be perpendicular to that corresponding surface, and hence on that point what kind of stress will be developed? It will be normal compressive stress. Why normal compressive? Because it will try to compress that point, it will tend to compress that point, and the forces will be perpendicular to the surface at that point. For example, if I take a small part of the fluid itself like this, so how will be the forces acting on that part? The forces acting on that part will be perpendicular to its area, and hence all these forces will provide what? Compressive stress to this part, normal compressive stress. Fine. So this was just some introduction about fluids. Okay. In the next section, we'll talk about what do you exactly mean by pressure of fluid at any point in the fluid. Okay. Okay. Now let us understand what is pressure at any point inside a fluid. Okay. Fine. Now I have considered this container. Inside this container I have taken some liquid. Okay. Now I am calling this as the liquid wedge. So I am considering that part of the liquid which has the shape of a wedge. So it is a liquid wedge. Now this liquid wedge is extremely small in size. So you can say that the liquid wedge is over here. So if you look at that distance, you will see nothing but a single dot. It is so small. I have just magnified the figure, magnified it enough so that you can see it clearly. Fine. Okay. Now since the size of the liquid wedge is very small, and hence I can say that each and every part of the wedge is at the same height from the surface. Fine. Okay. Now let us say rho is the density of the liquid. So the density of the liquid wedge will be also rho. Let us say V is the volume of that liquid wedge. Okay. Now as you can see that this liquid wedge is in equilibrium. That means all the forces that is acting on this liquid wedge due to the fluid from all the different directions should somehow cancel each other. Right? Now let us take cross section of this liquid wedge and draw it over here. Or you can say that what if I look this liquid wedge from this side, what I will see is this part. Okay, fine. Now these are the forces acting on this liquid wedge due to the surrounding fluid. Now we have already seen that the forces will always act perpendicular to any surface that we consider. Fine. And hence the forces acting on these walls of the liquid wedge are perpendicular to the wedge. Right? Okay. Now let us say this is F1 in this direction, F2 in this direction, F3 in this direction. So throughout this wall there is force F1. So I have shown this as the resultant of all of them. throughout this surface or this part is F2, throughout this part is F3. Fine. Now let us say this is the angle theta. So if this is the angle theta, by simple geometry you can show that the angle made by F3 with the vertical is also theta. Also, let us say that this surface area, that means this part of the wedge, this surface area has surface area A, and hence this will have surface area A sin theta because it is opposite to theta. This will have surface area A cos theta because it is adjacent to theta, right? Okay. Okay. So look here. So these are the forces F1, F2, F3 acting due to the surrounding fluid on the wedge. What about the weight of the wedge? That will be also considered. So the weight of the wedge will be mg in the downward direction. Now mass is nothing but density into volume. So mg is written as V rho g in the downward direction. But as we have said that the volume or the size of the wedge is extremely small, and hence this force V rho g will be negligible, and hence we will neglect this force. Okay? Okay. Now the forces remaining are just these forces acting on the wedge. Okay. Now let us balance them. Now the horizontal component of F3 will be what? F3 sin theta, because the component adjacent to theta is always cos theta. So the other component is sin theta. So F3 sin theta will be balanced by F1. F3 sin theta is equal to F1. F3 cos theta will be balanced by F2. F3 cos theta is equal to F2. Now here I am saying that divided by A sin theta on both sides, divided by A cos theta on both sides. So what we are left with will be F3 upon A is equal to F1 upon A sin theta. Here it will be F3 upon A is equal to F2 upon A cos theta. Now force per unit area is nothing but pressure. We all know that F3 upon corresponding area A is nothing but pressure acting on this surface area in this direction. So F3 upon A is nothing but P3. Let us say P3. And F1 upon its corresponding area. So F1 upon its corresponding area is A sin theta. So F1 upon A sin theta will be, let us say, P1, pressure acting on this surface in this direction. So as you can see, P3 has come out to be equal to P1. Now same F3 upon A was nothing but P3. Now what will be F2 upon A cos theta? F2 upon A cos theta will be P2, pressure acting on this surface in this direction. So as you can see from this result, P1 is equal to P2 is equal to P3. So the pressure acting from all the directions on this wedge is same. Did you get it? And hence pressure by itself does not have any particular direction. So pressure is a scalar quantity. Fine. So that is the things that we have written over here. Pressure is same in all directions. Getting this? And also the entire wedge was at the same height from the surface. So pressure of fluid at rest is same at all points if they are at the same height. Fine. What will be the unit of pressure? It is nothing but Newton per meter square, and its dimensions can be easily found out by putting N as kg meters per second square. Right? Also 1 Newton per meter square is called as 1 Pascal. Fine. Okay. Now if you want, you can note down all these things. Fine. Okay. Now look here. What we have said that if I take these points, so the pressure acting on these points will be same because all these points are at the same height from the surface. Another way to look at it is, suppose in the same way I consider a horizontal liquid cylinder. I am considering that part of the liquid which is of the shape of a cylinder, horizontal cylinder. The radius of that cylinder is extremely small. Fine. So again I can say that each and every part of the cylinder is at the same height from the surface. Now let us say this is point A this is point P. Point A and B are at the same height. Now, is this liquid cylinder in equilibrium? Yes, it is in equilibrium, right? It is there itself, not accelerating anywhere. So the forces acting on it in this direction should balance each other. Okay? Okay. The forces acting on in this direction should also balance each other. Anyway, so let us say that the force acting on A is Fa, the force acting on B is Fb. So since it is in equilibrium, Fa is equal to Fb. Right? Okay. Now let us say A is the cross section area of that cylinder. So divide both sides by A. Force upon area is nothing but pressure at point A. That will be equal to pressure at point B. Because they were at the same horizontal level. Right? Or they were at the same distance from the surface of the fluid. That is more appropriate way to say. Fine. So I hope you have understood what is a pressure or what is pressure at any point inside a fluid. Okay? Sure. Thank you.